Here we are again. I'm coming to you from a different camera angle today, from inside my steering wheel. So, I didn't like the one I had last time because it was just too close to my face, and I'm not what you would call man pretty, so I was a little self-conscious about that. Now we got some distance between us. Okay, so this is the second video in the series on natural theology, and so instead of giving these arguments for the existence of God in each video, I'm gonna talk about the premises individually in the video. So I don't know how long this is gonna go, but today I'm gonna talk about the universe, because we're gonna get into cosmological arguments. In previous videos, I made an argument. I talked about three different worldviews: idealism, naturalism, and dualism. And I argued that idealism and naturalism are false, which leaves us with dualism. Under dualism, both the physical universe exists and there's a realm of immaterial minds. So now, with the cosmological argument, I want to add to the immaterial world an additional mind, namely God. Boy, this is off to a rough start, I can tell. Keep in mind the purpose of this series of videos. So anyway, part of the reason I wanted to do the series on broad worldviews is to come to the conclusion that at least the universe exists. And from the premise that the universe exists, we can then start talking about the universe. And so that's what I want to do in this video. And what I want to argue, first of all, is that the universe has a finite past. There's a lot of people, a lot of Christian apologists, who will argue that the universe has a finite past and then jump to the conclusion, therefore the universe has a cause. So they're assuming that if it has a finite past, that it therefore came into being. I think that's a mistake. There's a step in the argument that they're skipping, and I plan to not skip that step. But on this video in particular, I'm just going to talk about the fact that the universe has a finite past. And there are at least 6 arguments I can think of to think that the universe has a finite past. I'm not going to talk about all of them today. I'm going to talk about 2 of them today. There are 3 scientific arguments and 3 philosophical arguments. There's probably more philosophical arguments, but anyway, I'm going to talk about, a lot of people put more confidence in science than they do in philosophy. For me, that's kind of a mistake. It depends on what it is you're trying to find out. I mean, obviously, there are some things that philosophy is not really equipped to answer, like the trajectory of a cannonball. What's his name? Aristotle tried to use philosophy to come up with the trajectory of the cannonball, and he was totally wrong. The boiling point of water, you probably couldn't figure that out using philosophy. You need science for that. But in general, for me, it doesn't matter whether an argument is scientific or philosophical. What matters for me is whether it's a sound argument or not. A sound philosophical argument will always trump an unsound scientific argument, and a sound scientific argument will always trump an unsound philosophical argument. So for me, it doesn't matter whether it's philosophical or scientific or mathematical or historical or whatever. The kind of argument it is doesn't matter so much as whether it's a sound argument. And in some cases, philosophy can give you a lot more certainty than science can. For example, in philosophy, you can reason deductively, and deductive reasoning can give you more certainty than inductive reasoning is. And a lot of scientific arguments are inductive, and they can only give you probabilities. And so there are some cases where philosophy can give you more certainty than science can. So concerning the beginning of the universe, I personally think the philosophical arguments are stronger than the scientific arguments, because the scientific arguments are they're based on provisional information. Most of the stuff we know in science is provisional. It can always be revised when we find out new information. It used to look like Newton had the laws of motion kind of nailed, and they really worked really well in our everyday experience. But when we started pushing them to the limits, looking at stuff that moves really fast, or the orbit of Mercury or whatever, there were gaps, there were holes. And Einstein came along and gave us special relativity. And special relativity did a whole lot better of a job at explaining things than Newton did. So basically our scientific knowledge is almost always provisional. And so any argument that we use, any argument for God that's based on a scientific finding, can't give us certainty. But if it turns out that we can use philosophical arguments to show that an infinite past generates contradictions, well, a contradiction is a necessary sign of error. And so if there's a contradiction in the very notion of an infinite past, that would prove with certainty that the past is finite. So I put more confidence in the philosophical arguments than I do in the scientific arguments. But let me talk about the scientific arguments anyway. And these arguments aren't purely scientific. I mean, they're more like philosophical arguments or speculative arguments based on scientific findings or whatever. Basically, it takes the scientific finding and extrapolates in a speculative way. So there are two things. One of them is the second law of thermodynamics. Now this, I think I mentioned in a previous video that between the ages of about 22 and 25, I was kind of agnostic. Well, the argument that I'm about to present right now is kind of what got me out of my agnosticism initially. And it's the second law of thermodynamics. The way it was taught to me back in nuclear power school was whenever anything happens in the physical world, energy is always being converted from one form to another. You can take heat energy, turn it into mechanical energy, and the mechanical energy can be turned into electrical energy, and electrical energy can be turned into heat energy, and etc. There's all kinds of energy conversions, but none of these conversions are 100% efficient, which means that if you have a closed system like a steam engine or something like that, and you have all these energy conversions coming on, the steam engine can't use all the energy with 100% efficiency. It's going to have to reject some energy, and it's going to have to take in some energy, because not all the energy is available to do work. So entropy is a measure of the amount of energy in a closed system that is not available to do work, and it always increases with every process. And so entropy is always going up, which means there's less and less energy available to do any work. And so that's one way of looking at entropy. Another way is like, you can look at entropy as like a measure of order. So like, say you got a bunch of clothes and they're folded up, and you put them in the dryer and you turn the dryer on. Well, the clothes are just going to become unfolded and rambled and all that kind of stuff. And they're probably just never going to fold themselves back up naturally. So everything kind of tends towards disorder. Another way of talking about entropy is it's a measure of the spreading out of energy. So like, say you've got a coffee cup in a box, and it's really hot and everything, and the rest of the box is cool. Well, heat will flow from the hot coffee to the rest of the room until it reaches equilibrium, so that the temperature everywhere in the cup and the room and everything is all equal. So it kind of spreads out. The heat spreads out. And the same thing if you got a pressurized pipe and you open a valve, the pressurized air will flow to the lower pressure regions until the pressure is equal through the whole thing. So you can think of entropy as a tendency for nature to reach a state of equilibrium. If you took a bunch of chemicals and you put them all in a test tube or whatever, it's going to pop and fizz and all do all this kind of stuff, and eventually it will reach a state of equilibrium. So with the second law of thermodynamics, everything's just kind of winding down. And so eventually that means that there will be no more energy conversions, which means that nothing else will ever happen. And so if this is just an inexorable law that just cannot be violated and just happens forever. Well, if the universe is infinite in the past, that means it's had an infinite amount of time to reach equilibrium. And you can think of the universe as a closed system, because the universe, if you define the universe as all of space, time, matter, and energy, just the whole kit and caboodle, then you can think of it as a closed system. So unless more energy gets created or something, or energy gets taken out somehow, then the whole universe is just headed towards what cosmologists call heat death or cold death. And that's just the idea that eventually the universe is just going to kind of fizzle out and nothing else will happen. And it's the unavoidable future that we all face. And so if the universe had an infinite past, then it should have already reached heat death. And the fact that it has not reached heat death shows that the universe must have had a beginning at some point in the past, a finite time ago. So there is one way to escape this, though. And this is something I did not know at the time. If I had known it at the time, it's hard to say whether I would have become a theist or not. But anywho, let's imagine, for the sake of argument, that the universe is infinite. And let's say that it's already reached thermodynamic equilibrium. Well, there's another way of looking at entropy that allows for the possibility of our universe existing, and it's to look at it statistically. So, like, take the shirts and the dryer analogy. The folding of the clothes is just one configuration that the clothes can take, but there's a lot of other configurations it can take. It could be wadded one way, wadded another way. You can have a sleeve hanging over this way or that way, or, there's all kinds of ways that the clothes could be. But there were far fewer ordered ways that they can be, like folded. They can be folded. There's a lot of different ways they can be folded in a neat and tidy way, but there are far more chaotic kind of ways that they can be. And so the reason why it tends towards disorder is because, statistically speaking, it's more probable that if you just turn the dryer on, that it's going to end up in one of the disordered states than it's going to end up in one of the ordered states. And so you never see it. You never turn a dryer on and then find your clothes folded, because that's so statistically unlikely. But the fact that it's unlikely doesn't mean it's impossible. There's still some non-zero probability that it could end up in some ordered state. And so if the entire infinite universe is in a state of thermodynamic equilibrium, there's still a non-zero probability that some small region of space can spontaneously become an ordered state. And the beginning of the universe was an extremely low entropy state, which, although extremely improbable, is not impossible. And so there is a way to avoid a beginning of the universe from the second law of thermodynamics. So although the second law of thermodynamics makes it look like the universe has a beginning, that's not certain. I still think that it's a decent probabilistic argument for a beginning of the universe, because we don't know that the universe is infinite. We can see the observable universe has a finite size, and so but the entire universe is beyond the observable universe, because the expansion of the universe is isotropic, which means that the farther away you go, the faster things are expanding away from you. And if they're so far away that they're expanding faster than the speed of light, then that light is never going to get to you. So there's a region of space outside of the observable space that we can never observe. So we really can't go out there and see how big it is. There have been some scientific investigations into whether we live in a closed universe or an open universe or a flat universe. Basically, they're trying to measure the curvature of space. If it's curved inward and it's closed, that means that it has a finite size. And if it's curved outward, then it's infinite in size. And if it's flat, I don't know, I guess it's indeterminate or something. But what they discovered is that as far as we can see, the universe is perfectly flat. but there's a measure of uncertainty in there. There are error bars in that calculation. And according to those error bars, the smallest the universe could be is 200 times bigger than the observable universe. The observable universe right now, I think, is something like 93 billion light years across. So now this is assuming, of course, that the curvature of the universe is the same everywhere. It may not be. So anywho, just based on what we know, I mean, we don't know how big the universe is, but if it is a finite size, and just based on, the finite amount that we're able to observe or calculate or whatever, the second law of thermodynamics does seem to point to a finite universe. It just doesn't point there with certainty. So anyway, we've gone 15 minutes. I was going to give 2 scientific arguments, but since we've gone as long as we have, I'm just going to leave it at that for this first one. And we'll talk about the second one in the next video. Thanks for coming. Hold on. Don't go yet. I wanted to add something to this this whole thing about the universe being infinite and our universe being just a random fluctuation of low entropy. If you go with that solution to avoid the beginning of the universe, it creates an interesting problem. I recommend looking at there's a channel on YouTube called PBS Spacetime, and they did a video on Boltzmann brains. I'm going to try to explain Boltzmann brains, but that video is probably going to do a better job of it. The idea of a Boltzmann brain is it's a thought experiment that is used by some cosmologists to adjudicate between different models of the universe. If you have a model of the universe that generates Boltzmann brains, then there's probably a flaw in your thing, because what it means is if we take this model of the universe that I proposed earlier, which is the idea that we live in an infinite universe that's already in thermodynamic equilibrium, and you have random fluctuations of low entropies. Well, if that's true, then we should expect that there would be more fluctuations. There would be more small fluctuations of low entropy than there would be big fluctuations of low entropy. In other words, like I said, this depends on a statistical model of the second law of thermodynamics. And so the lower the entropy, the less probable the fluctuation will be. Well, the beginning of the universe had just an unimaginably low entropy, because the universe has been around for 13.82 billion years, and there's all these stars going on, there's all these life. I mean, just one individual human life has extremely low entropy because it's a very ordered state. And so if this is hard to explain. So if you explain the universe in terms of low entropy, well, it's a lot more probable that you're just a single brain that randomly fluctuated into existence, and it's structured in such a way that it produces perceptions of an external world that's not really there. And this just happened a couple of seconds ago. These Boltzmann brains, they just kind of fluctuate into existence and then fluctuate out of existence. So at this very moment, you could be a Boltzmann brain who just came into existence, and you're just about to go out of existence, or actually right now. So that is statistically more probable than a whole universe, because the entropy at the beginning of the universe is far lower than the entropy in a single brain. And so if we've got this infinite universe that has random fluctuations of low entropy, that there will be far more individual Boltzmann brains then there will be whole universes like our whole, big bangs like we observe. So with that being the case, it's more probable that you're one of the Boltzmann brains than it is that you live in a real universe the way it appears to be. And so that's a weakness in that solution. So that's another reason to think that the second law of thermodynamics points to a finite universe. So because I mean, you could bite the bullet and say, okay, well, I guess I am a Boltzmann brain. But that's just, just if you want to be a reasonable person, that's just kind of absurd. And so if you want to avoid just being silly or being absurd, you should say, okay, well, I'm probably not a Boltzmann brain. But the only way you can say that is to reject this model of the universe that says it's more probable that you are a Boltzmann brain. You know what I'm saying? So that's a problem with that model of the universe, which means that model of the universe, while technically it does remove certainty from the argument from the beginning of the universe, still probably the probability is in favor of there being a beginning of the universe because of the second law of thermodynamics. So I still think the second law of thermodynamics is a really good argument for the beginning of the universe. It's just doesn't give us certainty. That's all I'm saying. So there you have it.